All right, guys, take a look at question number 6 from our multiple choice section today. A lot of you guys already got to this one, so you can fast forward if you already passed number 6. But on this one, you're going to be given the graph of f prime, and they're asking where is the function concave up? Well, since the second derivative is the slope of the graph that they give us, if the second derivative is positive, that means that the graph they give us would have a positive slope, which means it would be increasing. So if the second derivative is positive, that means the graph we're looking at has a positive slope, which means that that's where f would be concave up. And then contrary-wise, if the second derivative is negative, which would make the graph concave down, our graph would be decreasing at that point. So that's for number 6. Let's go ahead and take a look at 7. So this question is asking us, where is the graph concave up? You can actually use the same principle that we talked about on number 6 to answer this question. You don't really need to use the equation at all. You could. So what you could do is you could take this equation and do the second derivative and do the a number line test. But like I said, I wouldn't advise it. I would solve it just the same way that you did question 6. Just look for where it's increasing and decreasing, and that tells you where it's concave up or concave down. All right. Question number 8. We're going to, the question is asking you in which of the equations given will the second derivative test be inconclusive? Well, the second derivative test is inconclusive anytime the second derivative is equal to 0. So what you're going to do is you're going to find the second derivative for each equation. Now, if I remember right, they give you the function, and then they give you the first derivative. So you need to find the second derivative yourself. Then you plug in the 2, and you see which one gives you 0. If it gives you 0, then the second derivative test is not conclusive. Now, my hint to you is to start with the one that has the easiest derivative to find. Some of them were pretty nasty from what I remember. So start with the easy ones and you might luck out. Okay, let's go ahead and move on to the next question. All right, so for this one, I'm just going to do the actual problem that they gave you. It's just kind of like once I explain it, the answer is kind of obvious. But before I explain it, it's not really very obvious. So let's kind of go through it here and take a look. So we've got the graph of f double prime here. And they tell me that there's only one critical point. That's actually a pretty significant fact that they're giving us here. And they tell us that it happens at x equals 6. So at x equals 6, that puts my dot right about there, which means that f double prime, because this is the graph of f double prime when x is equal to 6 is approximately 3, it looks like to me. So that's a positive number, which means that f is concave up at x equals 3. Now, I'm sorry, 6. Not only is it concave up, but that's a critical value, okay? And a critical value is where the first derivative equals 0. So that means that f prime of 6 equals 0 if it's a critical point, okay? Now, what's significant about that? Well, that means that it's the bottom of a curve, and it's concave up. So this is what my graph would look like. This way, the first derivative of f, this is a graph of f, kind of. At x equals 6, f would have a flat tangent line because the first derivative at 6 would have to equal 0. And then also, the second derivative is positive, so it would have to be concave up, which means that we have a relative minimum there. But here's the thing. So that's basically just the second derivative test, by the way. However, there's more to it. Since there's only one critical point, that means that this graph will never curve again. So it only has one curve here, and after that it stays the same, which means that the graph never curves back down or anything like that. It's just going to keep going in an upward direction. So not only is this going to be a relative minimum, but in fact it's going to be the absolute minimum. It can't be any lower. And that's because there's only one critical value. Now that's, like I said, that's kind of a sneaky little strange problem, but there it is. All right, let's go take a look at 10. So what I gather from this is that we're given a graph of f prime and they're asking you, when is f increasing and concave up? So when is f increasing in concave up? Well, f is increasing when the first derivative is greater than 0. Now, since this is a graph of the first derivative, that means anywhere f prime is above the x-axis. Okay? Secondly, f is concave up anytime its second derivative is 0. Now, since the second derivative is the slope of the first derivative, which is our graph, if the second derivative is positive, that means my graph of f prime has a positive slope, which means that it's increasing. So if I want to find where f is both increasing and concave up, I'm looking for where the graph is above the x-axis. In other words, f prime is greater than 0, and it has a positive slope. In other words, f double prime is positive. So I'll leave you to that. Let's take a look at number 11. All right, guys, so for question 11, they give you a table, and they ask you some questions. They ask where are there some relative extrema, and also where are there some points of inflection. So let's take a look here. Now, the first thing you want to do is you want to find anywhere where this first derivative is 0 or undefined, because these are critical values. And that's where the relative extrema can possibly occur. Now, once you've found those, a relative max occurs when it changes from positive to negative. So, if you had f prime, let's just say that this was 3, this was 0, and this was negative 5. Well, here's my critical value, and as you can see, we went from a positive to a negative. So the x value here would be a relative maximum point, okay? Or it's where the max occurs. And for minimums, it's whenever it changes from negative to positive. Now, how do we find the points of inflection? Well, you want to find all the places where the second derivative is 0 or undefined. Those are possibly points of inflection, but they're only points of inflection if f double prime changes signs at that point. So that's how you can find relative extrema and points of inflection on a graph. All right. Similar question, but this time instead of a table, we have a graph. So they're asking me to find points of inflection and relative extrema. So let's see if we can find the relative extrema first. So a relative max and a relative min. Relative maxes happen anytime f prime changes from positive to negative. Relative mins happen anytime f prime changes from negative to positive. Okay? Now this is a graph of f prime over here. And here's my x-axis. So where do the relative extrema occur? The relative extrema are going to occur anytime f prime changes from positive to negative or negative to positive. So here's one right here. At this point, x equals 1, we're going from below the x-axis to above the x-axis. So that's negative to positive, so that would be a relative min at x equals 1. We have another one over here. That's also going from below to above. So there's another relative minimum at x equals 8. Now, I don't see any relative maxes. I don't see anywhere on here where it goes from positive to negative, so none of those seem to exist. All right, now let's consider the next question, which is points of inflection. Points of inflection happen when f double prime changes signs. Now, what's important to understand here is that since I'm looking at a graph of f prime, f double prime is the slope of f prime. So in other words, we're looking for anywhere on this graph where it changes signs. All right, let's see. So where does the slope change? Well, the slope changes right here. We go from a positive slope to a negative slope there. So we would have a point of inflection at x equals 2. Here's another change. We go from a negative slope to a positive slope there. So that's at x equals 3. And up here, we go from a positive to a negative slope, so that's another one at x equals 5. Lots of points of inflection here. And then we have another one down here at 7. So there's lots of points of inflection. Now I just realized I actually did leave out a relative max. There is a relative max. The relative max occurs anytime f prime changes from positive to negative. And I saw one that I missed just because it doesn't look quite normal, but it's right here. We go from positive to negative. I think I meant to have this stretch over to here like this. But as you guys can see, at x, I'm going to say that at x equals 6, the graph goes from suddenly being positive to negative. Now the derivative's not defined at 6, but that's okay because that's a critical value also. And all that matters is jumping from positive to negative. So I take it back. There actually is a relative max. There's a relative max at x equals 6. So we'll go ahead and put that there as well. So we have a relative max at x equals 6, two relative minima at 1 and 8, and then we have a ton of points of inflection. So anytime the second or the first derivative goes from positive to negative or negative to positive, you get a relative extrema. And anytime the second derivative changes from positive to negative, you get a point of inflection. On this graph, f prime changing means it goes from below to above the x-axis, and for the slope changing, that's when f double prime changes its signs. So let's go ahead and move along here. We'll look at our FRQs. All right, so they tell us here that the number of mosquitoes in a field after a major rainfall is modeled by this function here, where t is the number of days after the rainfall ended, and time is between 0 and 18. So for part A, using the correct units, interpret, so there's 2 points right there on this FRQ, interpret the meaning of this in the context of the problem. So M is the number of mosquitoes. So what is M prime? Because that's what we have here. What is M prime? M prime is the rate of change of the number of mosquitoes. In other words, how fast is the population increasing or decreasing? So that's what that would tell me. This one's units up here would be in mosquitoes. This one here, the units would be mosquitoes per, what are we measuring in here? Days. So mosquitoes per day. All right, so if M is the number of mosquitoes, M prime is the number of mosquitoes per day. All right, so now let's interpret this expression over here. This number in here is the time value. So at t equals 15 days, the mosquito population, is it increasing or decreasing? It's decreasing because the derivative is negative. So at t equals 15 days, the mosquito population is decreasing at a rate of 171 mosquitoes per day. That would be our interpretation. Okay? Anytime you have an interpretation, you need to have 3 pieces there. You need to have your input units. You need to have your output units. And then, of course, it needs to incorporate the rest of the story, which is about mosquito populations. So, all right, let's move along here to part B. Based on the model, what is the absolute maximum number of mosquitoes in the field over the time interval from 0 to 18? Justify your answer. Well, anytime you want an absolute max, we learned today, or we were reminded today that that's a candidate's test. So candidate's test, we're going to put T here. We want to find the maximum number of mosquitoes here, and we're going from 0 to 18. Now we need to find our critical values, so I'm going to take the derivative of this expression here and set it equal to 0. All right, now all of these numbers can be divided by 3, and I actually don't like having negatives in the front either, so I'm going to divide everything by a -3. There's that. I'm going to go ahead and factor this. Now let's see, 48. Now if I set both of these equal to 0 and solve, this one will give me 12, this one will give me -4. Now I don't care about -4 because we're only going from 0 to 18, so I only have one critical value that I actually care about here. And then we're going to simply plug them in to this equation up here and find out which one is the greatest number of mosquitoes. And that's it. I'm going to not do this part just for the sake of time. You guys can handle that. Just plug it in your calculator and get the max, and we'll move on from there. All right, let's go ahead and hit up part C. It says, for what values of t is the rate of change of the number of mosquitoes? Now, let's translate that. For what values of t is m prime of t? So we're asking a question about m prime. So for what values of t is the rate of change of the number of mosquitoes, m prime of t, increasing? So what they're really asking is when is m prime increasing? Well, m prime increases when its slope is positive, right? So m prime increases when m double prime is positive. So what we're going to do is we're going to find our second derivative, and we're going to do a number line test to find out where the second derivative is positive. Okay, so here we go. We've already found our first derivative, but I'll write it up here again. Now we need to find our second derivative. We're going to set it equal to 0 and solve. If I solve that, I end up with t equals 4. And then I'm going to do a number line test. 4 goes here, 0 goes here, and 18 goes here. Now let's plug in some test numbers. I'll plug in 1 to my second derivative, and I'll plug in 5 to my second derivative, and we'll see what we get. So if I were to plug 1 into my second derivative here, I'm going to end up with a positive number. If I plug in 5, I'm going to end up with a negative. And so the second derivative is positive on this interval here. So typically they wouldn't want you to just have an answer. So it doesn't say give an explanation, but I'm going to give an explanation anyway. So we would say since m double prime of t is greater than 0 on the interval from 0 to 4, m prime is increasing on that interval. You would still need to show all the math work that I just showed, but this is technically like your explanation. Okay? All right, let's go ahead and move along. Part D. All right, so for the time interval from 0 to 18, the number of bats in the field is modeled by the differentiable function b. So b is the number of bats. They tell us it's differentiable. It tells us that b is a function of the number of mosquitoes. Okay, so that means that b of m, it's a function of the number of mosquitoes, which means that technically it's b of m of t, because the mosquitoes is a function of time. So in other words, what b is determined by what m is, and what m is determined by what t is. That's what it means when they say that b is a function of. That means the input variable is m. So b is a function of the number of mosquitoes in the field. Based on the models, write an expression for the rate of change of the number of bats in the field at time t equals a. So the first thing I'm going to do is I'm going to take the derivative of this, which is going to require the chain rule. b prime of m of t times m prime of t. Now they want me to do it at t equals a, and so all I have to do is put an a in there. Now I think that if you were to look this up, this is my answer, by the way. So you have to understand that b as a function of the number of mosquitoes means this, which means that you're going to have to do the chain rule. Now another way that this could possibly be done is in the following way, but this will look a little bit weird to you guys because I didn't do it this way myself in class too much, but I have seen them write it this way. So this is what I got, but you might see them write their answer this way. The derivative of b with respect to m times the derivative of m with respect to t. Okay, so b is a function of m and m is a function of t. At x equals, I'm sorry, I should say t equals a. So I don't use that notation a whole lot for my chain rules, but I have seen textbooks do it. So, and just in case you get a question like this as a multiple choice, at least you've kind of had some exposure to it here. So hopefully that was helpful. But anyway, that's where we're going to call it quits. So hopefully it was helpful. We'll see you guys next time.